Let's explore the fundamental concepts of process creation and termination in UNIX-like operating systems. In this presentation, we will cover the fork, exec, and exit system calls. These system calls are the building blocks for managing processes in these systems. These functions are very useful and important in operating system design. Let's dive in and understand how these calls work together to bring programs to life and manage their life cycles. Here we are going to discuss the fork system call. The fork system call is the primary way to create a new process in UNIX-like systems. When a process calls fork, the operating system creates a nearly identical copy of that process. This new process is referred to as the child process, and the original process is known as the parent process. After the fork call, both the parent and child processes execute concurrently, meaning they run independently and potentially at the same time. Each process has its own separate memory space. Although the child process starts as a duplicate of the parent, it has its own distinct copy of the parent's data, heap, and stack segments. Any modifications made by the child process to its memory space will not affect the parent process, and vice versa. Now let us discuss return values of the fork function. The fork function returns different values based on whether it is running in the parent process, the child process, or if an error occurred. In the parent process, fork returns the process ID, or PID, of the newly created child process. The PID is a positive integer that uniquely identifies the child process within the operating system. In the child process, fork returns 0. The child process can use this 0 return value to determine that it is indeed the child process, and then execute different code accordingly. If the fork call fails for any reason, such as insufficient memory or reaching the limit of processes a user can create, it returns -1 to the parent process. No child process is created in this case, and the parent process should handle this error appropriately. It's important to note that after a successful fork, both processes continue to run the same program, but the different return values from the fork call allow them to differentiate their behavior. Let's examine a practical example of how fork is used in a C program. First, we include the standard input-output header file, standard library header file, and the unis.h header file. The unis.h header file contains the fork function. Inside the main function, we declare a variable named PID of type PID_t. Now we call the fork function and assign the result to the PID. If the value of PID is less than 0, it means that the fork call failed, and we print an error message to standard error. If the value of PID is equal to 0, it means that we are currently running in the child process, and we print a message to standard output indicating the process ID of the child process using the getPID function. If the value of PID is greater than 0, it means that we are running in the parent process, and we print a message to standard output indicating the process ID of the child process. Keep in mind that the order in which the parent and child processes execute is non-deterministic, meaning you cannot predict which one will run first. However, the fork call ensures that both processes continue execution from the same point in the program, but with different process IDs and memory spaces. Each process has its own memory space, and the child process gets a copy of all variables from the parent. Let's explore the exec family of system calls. The exec family of functions are used to replace the current process image with a new program. When one of these functions is called, the current process's code, data, heap, and stack are replaced by those of the new program. The process ID remains the same, but the program being executed changes. There are several variants of exec, each with slightly different ways of specifying the program to execute and its arguments. Execl takes the path to the executable file as its first argument, followed by a list of arguments that are passed to the new program. The list of arguments must be null-terminated. Exec takes the path to the executable file as its first argument, and an array of arguments as its second argument. The array must also be null-terminated. Execl is similar to execl, but it searches for the executable file in the directories specified in the path environment variable. Execf is similar to execf, but it also searches for the executable file in the directory specified in the path environment variable. Execl allows you to specify the environment variables that should be passed to the new program. Exec is the most general form of exec and allows you to specify both the arguments and the environment variables for the new program. On success, the exec functions do not return because the current process is replaced by the new program. If an error occurs, they return -1, and the calling process remains unchanged. Let's delve into an example of using the exec function in a C program. The exec family of functions replaces the current process image with a new process image, and the new image is constructed from a regular executable file. In this example, we use the execl function to replace the current process with the ls command, which lists directory contents. We pass the path to the ls executable, which is typically located in the bin directory, along with the arguments to the ls command, which are ls and l. The ls argument is conventionally passed as the first argument to the new program, and l is an option that tells ls to list files in long format. If the execl call is successful, it does not return to the calling process, as the current process is replaced by the ls command. Therefore, any code after the execl call will only be executed if the call fails. In this case, the printf statement will not be executed if execl succeeds. After the execl call, the original program's memory, text, data, and heap are replaced by those of the ls command. Now let us discuss process termination and the exit system call. The exit system call is used to terminate the calling process immediately. When exit is called, all open file descriptors are closed, any child processes are inherited by the init process, and the exit status is reported to the parent process via the wait or waitpit functions. The exit status is an integer value that indicates whether the process terminated successfully or encountered an error. A status of 0 typically indicates success, while a non-zero status indicates failure. The _exit function is a lower-level call that does not perform cleanup operations such as flushing buffers or closing files. It is typically used in situations where a process needs to terminate immediately without any further processing. Here's a small C program that demonstrates the usage of the exit function. In this program, we attempt to open a file named data.txt. If the file cannot be opened, we print an error message to standard error and exit with a status of 1, indicating failure. Otherwise, we would process the file, close it, and exit with a status of 0 indicating success. Let's explore the Fork-Exec Pattern. The Fork-Exec Pattern is a common process creation technique used in UNIX-like systems. It involves first creating a new process using fork, and then replacing that process's image with a different program using exec. The fork call creates a new process that is a duplicate of the calling process. After the fork call, both the parent and child processes continue execution. Typically, the child process then calls one of the exec functions to replace its process image with a new program. This allows the child process to run a different program than the parent process. The Fork-Exec pattern is useful because it allows a process to create a new process and then replace it with a different program while maintaining the parent-child relationship. The parent process can continue executing its own code while the child process runs the new program. Let's tie everything together with a complete example demonstrating the Fork-Exec exit pattern. This pattern is fundamental to process creation in UNIX-like systems. This example shows how to create a child process using fork, replace the child process's image with a new program using exec, and then have the parent process wait for the child to complete before exiting. First, we create a new process using fork and check for errors. If the fork fails, we print an error message and exit. If the fork is successful, we check if we are in the child process or the parent process. In the child process, we call execl to replace the current process's image with the ls command. After the execl call, the child terminates with exit. In the parent process, we call wait to wait for the child process to complete. After the child process completes, we print a message indicating that the child has completed. So fork creates a new process, exec replaces the current process image with a new program, and exit terminates the process. The wait call allows a parent to wait for a child process to terminate. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.